point out. Two things I want to point out. First of all, I've already pointed this out once. I didn't do as good a job this time because I was in a hurry. But we were aware of this idea, right? Energy levels, first energy level, second energy level, third energy level. Now it starts getting a little wishy-washy over here because of that overlap of the orbitals that we talked about, okay? But you can kind of clearly see this. So once again, I think we did this yesterday, I'll do it again today. Kayla, how many valence electrons does chlorine have? Did I do this with you guys yesterday? I meant to. Kayla? No, it doesn't matter. Just look up there. Valence electrons.
7.
Excellent. Outermost energy level, right? Lauren, how many valence electrons for calcium? This is a no-brainer. It is a brainer. Calcium, that would be the Ca.
Oh, 2.
2, very good. Yeah, you weren't awake. You just went right down to phosphorus, didn't you? And let me see. Gosh, I'd like to pick on a guy, but there aren't any. Zach, how many valence electrons for? Ooh. Wow. Guess all we have. Phosphorus. 5. That is 5. All right, moving on. Next, watch this. How many electrons are in the purple box? 10. What element might be the one with 10 electrons? Would you agree with this one also?
Yeah.
How many electrons are in the purple box? 18. What element might have 18 electrons? How many electrons in the purple box? How many?
36.
36. What element might have 36? How many electrons in the purple box? Is it? Recounting? How did you figure that out then? Is it 54? Are you sure? Zach, are you sure? And what element is that, Zach? Xenon, right? Interesting. What can you say about all the orbitals up to this point? Full. What electrons are being represented here? Valence electrons. What about here? What about here? Valence electrons. Well, this is a little beyond that, but remember this is a transition metal. You can't do the valence electrons that way anyway. Interesting. So really, which electrons do we care about as far as chemical reactivity is concerned? Does anyone know? Valence electrons. So really, who cares about the rest of those, right? Kind of. Well then maybe, instead of writing out all the electrons that we really don't care that much about, what if we do this? Or maybe this. Or maybe this. pretty quick way of doing an electron configuration, isn't it? What do you guys think of that? Okay, well that's part 2A, or sorry about that, 2B. Okay, remember we had electron configuration notation, right? Or otherwise known as SPDF, okay? However, if we really only worry about the valence electrons, which are the ones we care mostly about anyway, what we can do is put, well, actually the electrons that I put in purple boxes are called the core electrons. So as we progress here for the next couple of weeks, we're going to use the words core electrons and valence electrons. You just have to know what that refers to. You see, this is Rice. That is Andrew. We must have worn him out last night. And look, everyone, Libby's here today.
Oh my gosh, I knew you were gonna say.
And I'll continue to do that all year long. Alright, so anyway, this is called, there's actually two names for it. Technically, it's called, technically it's called noble gas configuration, what I just showed you, because we're showing the noble gases that are involved, or shorthand notation, either one. So get used to both phrases, shorthand notation, noble gas notation. So I may be a little repetitive today. Now, if we're going to do molybdenum, obviously, what would it look like? Well, it'd be krypton in brackets and 5s2, 4d4. And finally, if we were going to do your europium, you would do xenon in brackets, 6s. And depending on your periodic table, either 6s2, 4f7, or 6s2, 5d1, 4f6, either way. Okay. You guys like that? Now the question becomes, once again, how do I do that without having all of that other stuff available, right? And because that's, you've noticed that little progression, we've kind of been referring back to stuff we've previously done, right? So it doesn't seem to be much of a shortcut. Okay? But I've been trying to give you guys little hints to get there. Well, here's what you do. Pick an element, and the element, Bella. Potassium. Oh, you really picked a tough one. Just kidding. So what you do, if you want to use the noble gas configuration or shorthand configuration, is you locate the element you're in question and start working your way backwards until you run into a noble gas. Now, Bella didn't make it very hard this time. Here we are at element number 19, so we work our way back to element number 18, which in this case is argon. We know every single orbital up through that point is completely full. That's the whole reason for the noble gas, right? Okay. And so all we have to do is write argon in brackets, and then 4s1, right? That's all you would do. Pick another element, Maya. You should. Oh, woke Maya up. What's that? Okay, we're not going to do that for oxygen. Here's why. If we were going to do oxygen, previous noble gas would be what? Helium. Now, watch this. That's the noble gas configuration for helium, right? Remember I said this can sometimes be called shorthand notation, right? There's noble gas configuration for helium. How many marks did I make? 3. Or I could do this. How many marks did I make?
6.
What's that? That would be 4. 1, 2, 3, 4.
If you count it.
I'm not counting those. Oh yeah, this, okay. How many?
Characters?
One way or the other, I think it's clearly visible that this is not much, but harder to write than this. Would you agree? So I'm not going to say this is shorthand notation. So we're not going to use that for the group 2, or sorry, that period 2. It's pointless. Oh, iodine. Here's a good one. What are we going to do? Go back to the previous noble gas. 37, 36. We would write krypton in brackets, and then work our way forward. So we would write 5s2, 4d10. Ah, good thing we did this. 5p5. Remember, the s's and the p's are the representative elements. They coincide with the period numbers. So 5s2, 4d10, 5p5. Pretty darn easy, isn't it? Okay. So that is like, so we had orbital notation, which was technique 1. We had electron configuration notation, which was, part A, which was the what we had done up here, and then finally part B is the noble gas configuration or shorthand notation. Yeah.
Are we gonna do all three of these at once?
Oh, but wait,
Oh my God.
there's more. Kayla, would you like me to make your life even easier than this? I mean, is this easy? Would you like it to be even easier? Okay. Hey, there's Bryce.
Hey, Doug.
Are we doing a trade for Livy or what?
Sure.
No? Okay. I mean, I can't have a full class. All right, moving on. Lastly, and here's the actual one. Oh, I erased one that I didn't mean to erase. Here is one that you guys actually knew before you ever walked into this class. This is the last one. Now, this has a fairly severe, not severe, it has a limitation. The electron dot or Lewis dot notation has a limitation. It only is useful for the representative elements. Lewis dot notation or electron dot notation is only useful for the representative elements. Even though I already mentioned it today, let's remind ourselves, when I say today, I'm talking less than 2 minutes ago. What are the representative elements? What's that? The S and P orbital filling groups, or, you know that now, that's awesome. Seriously, that's really good. Or, what did we know them before? The group A elements. So notice we've got 3 different ways of doing it now. Before we used to call them the group A elements, right? That was back at the beginning of the year. And then we said, oh, these are the representative elements, and now Caleb just said it, these are the S and P orbital filling elements, right? Now, for only filling S and P orbitals, what's the maximum number of electrons I can have? 8. There's group 8A, right? 1 through 8. The maximum number of electrons that we can have is 8. Look. S and P, how many electrons? 8. S and P, how many electrons? 8. S and P, how many electrons? Well, 2 and 6 is 8, okay? S and P, how many electrons? 8. Doesn't matter. When you're talking S and P, it's 8 electrons, right? So we're going to take advantage of that. Now, I'm going to use, as an example, the element X. Everyone knows what that is, right? Emily, what's that element? Oh, Emily? There is no element. Okay. Moving on. All right, moving on. And so here is technically the way this is done. We're going to put the electrons in a very similar manner that we did the orbitals, S, P, X, P, Y, P, Z, okay? Remember what we did is we went 1, 2, 1, 1, 1, 1, 2. Remember, don't write that down. Remember how we did that? Following Hund's rule, right? We're going to do the same thing here, except we're going to use the top representing that at, whoa, I did this wrong. We're representing the left-hand side as the S, Px, Py, Pz. Except I did that backwards. That's all right. So, for example, if we're going to do the electron configuration for, say, sodium. I messed this up. My bad. Darn it. I just got to fix it. We're going to do the S here, Px, Py, Pz. My bad. Okay, so if we're going to do the electron dot or Lewis dot for sodium, now remember, the limitation is we're only looking at the valence electrons for the representative elements. How many valence electrons does sodium have? Everyone together now? One. Done. You guys have done this before, I think, right? You never knew why you were doing it, but now you know. Maybe. I don't know. That's it. Here, let's make Kayla happy. You had picked potassium before, hadn't you? What was that? What did you pick? Oh, I didn't make you pick one? Pick an element.
Cobalt.
I knew it.
Oh,
I
wait.
knew she was going to do that. I knew it. I knew it. I thought you were going to say iron. I really thought you were going to say iron. I knew you were going to do that. Silicon, you say, right?
Yeah.
Okay, so how many electrons does silicon have? Valence electrons. 4. Where's the first one going to go? S. Where's the second one going to go? S. Where's the third one going to go? Px. Where's the fourth one going to go? Py. Boom, there's silicon. Kelsey, you look like you would like to pick an element. Don't get yourself in trouble here. Don't get fired.
Let's see. No. Oh, okay.
She just got fired. You got fired. What'd you say? Roaming. Whatever. How many valence electrons, Kelsey? Oh gosh.
Oh my God. Why would you pick one?
The reason is fairly clear. What? I'm still waiting for an answer. Say what Caden said. Good. Nice job, Caden. So, 2 in the S, 1 in the Px, Py, Pz, and then back to the Px, Py. Pretty easy, isn't it? Okay. That's it. Now, just for fun, what are the 4 quantum numbers for that electron? Remember I said just for fun. This is fun. What are the 4 quantum numbers for that electron? Now, I'm extending you on this one. This is a thing. Well, remember my quantum numbers are n, l, m sub l, and m sub s. You guys thought we were done with that, didn't you? We haven't even touched on it yet. So where is that electron? Yes. Well, okay, which PY? What's that? 2PY. Anyone concur? No one knows whether to concur or not. Okay, I'll show you where 2PY is right now. 2PY is right there. So you were close. Here's what you did. You went 1, 2. I swear that's what you did. Okay? Everyone thank Jacob for making that mistake. Say thank you, Jacob. Here's why. Because there's going to be times when I'm going to ask you questions like, identify the element in period 3, group 2A. Oh, sorry about that. Let's do it this way. Period 3, group 5A. I can tell you what half of you would have done this. Okay, period 3, or sorry about that. What did I say? Period what? Period 3, group 5A. A lot of you would have done this. Period 3. Wait, sorry. Group 5A. Okay. 1, 2, 3. That's now some of you guys would have done it. I'm telling you right now, you would have done it. Okay? You can't start here because this is period 1. You guys with me on that? Okay, so anyway, because that's what you did. He said 2Y, because what he did is went 1, 2. Oh, that's period 2. It's actually period 3. So it's a 3PY. Now, is that the first time we're in that orbital?
Yes.
Is that the first electron in that orbital? Right, so that means its arrow is pointing up. Are you guys with me on that? See that all this needs to be in your brain. Okay, so now we got a 3py orbital with an arrow pointing up. With that being said, what are the 4 quantum numbers then for that electron? Everyone together now for the N. 3. How about the L?
1.
Well, remember, a p orbital is an L of 1. What is the M sub L? Well, remember, the possible values for M sub L are -1, 0, +1, or in other words, X, Y, Z. Therefore, this is a 0, and the M sub S is, it's an arrow pointing up, +1/2. There you go. There's the 4 quantum numbers for that electron. Now that's putting things together, isn't it? Yes.
How did you get N?
It's in the 3rd energy level. Okay, well, with that being said, we need to practice. Would you guys like to practice?
Yes.
Oh, but wait, you guys wait till you see this practice. Where'd it go? I wonder if oh, there it is. Found it.
Oh gosh, he could pass me. That's probably going to be on the exam.
How did you get the letters?
I know. I know. None of them. I don't like that. Those are up to 100. 25%. That's a lot. He could pass me. Q equals N. C delta T. Days.
Just this line right here.
We thought this was
This is a lot of stuff.
Okay, I'll go ahead and get you started on the other thing first because the copier's not working. There's 2 parts to this assignment. I was going to have you do this first part on the back of the other one, but you guys just have to do this on a separate piece of paper. Okay. Where'd my little partial piece of paper go? those are the elements. I would like you to do the indicated type of electron configuration. I'll see if I can make a copy of everything. You go ahead and get started on that.